Whoops. Darn. I think that made sense. Bummer. Bummer. I didn't get that. You want to do that again? For the camera? It's like take two.
Yes.
All right, so that works really well for disks and for two-dimensional rolling. Okay. Now what about 3D? Let's go back to the drawing board. So if you've got a sphere. So now with our sphere, we got a couple of things that we need to handle. All right, I've got a sphere rolling on a surface. Okay, my surface A. And then with this, let's make our chart where let's say the sphere, actually tell me what types of kinematic comments can we make about motion comments about a sphere rolling on a surface? Make my surface here too. There we go. Sphere rolling on a surface. Okay.
Mass is translating.
Okay. Center of mass is translating. That becomes really helpful when you make this operational, right? Okay. Center of mass is translating.
But it's only translating in that plane, like it's not going up and down. Like some gravity is going to hold it down.
Okay, so we've got something here that I think is important. Okay, the center of mass is translating. True. Okay. I mean, in this case, is the center of mass translating? Okay, but I think you wanted to say something that Hannah filled in, right? Yeah, we've got a constraint. Okay, and so that's the difference between the floating ball and the rolling ball, right? Or even the sliding ball. Right? So what is that? What are we actually saying here? How do I make this a not floating ball?
The position BCM to BN is constant.
Okay, you could say the position BCM to what?
What is that? BA.
BA. Okay. You can say that's constant.
Yeah.
Okay, how would we do that? If we're going to say that's constant.
Equals Y, is that NY?
Equal
Constant.
Y.
I don't know. I mean,
You get somewhere.
Yeah, like it'll be like the radius in our NY direction, so it's already from there, that's us.
Okay, yeah, well, that works pretty well for a sphere. Okay, what about this guy?
that's convex.
Give me, like, if I should have brought that rattle back, right? If I had a banana and it's rocking back and forth, can we say something about the BCM with respect to BA? Is that going to be constant? So like if I let's do like the stressed potato, the kidney bean, right? And then now there's my contact, right? And then let's say it's a kidney bean that's weighted more to this side. I got a center of mass there. Let's be a little bit generic. We're trying to keep it from floating.
You have to figure out to get like a range of where it can be. This kid's an example. It's just that it's always in contact.
So that's what we're wanting to say. Okay, that's always in contact. Okay. And so I want to back away from the center of mass. Okay, now you are thinking correctly in saying I need to use points here. Okay. And so you can say, all right, I got a center of mass, but let's deal with this stuff down here. Okay. And so if that's the case, what point is it that we need to ensure that's in contact? How do we make that happen? It's the my rolling thing is not floating constraint.
Seems like a position vector.
Position vector sounds great to me.
The position,
Okay.
BA to AB.
Okay. BA to AB.
Yeah.
Zero
Vector.
vector. Okay. Yeah. Yeah. Let me give you another way to write it. Okay. Let's do V sub A. I like that. I'm like, I just want to make a point A naught is equal to 0. Right, and then I want to dot it with the AY direction. So what have I just done there? Yeah. It's the height, but from what point? From A naught.
It's any, okay, that one.
Yeah, so, yeah, we're saying it's a flat surface, right? I got my flat surface. Okay, A naught, okay, and we could, if we want to get more specific, we could do the A sub B. I think that would work just fine, as long as you know where it is. If it's a flat surface like what we got here, okay, because we're rolling on a plane, you make it from point A naught. And then if this is normal to the plane, you're good. Okay.
I feel like I wanna say that it's 0 after the dot product, but not necessarily, you know,
Got it.
like, do you see what I'm saying?
I do, yep. That's it. Yep, so that's actually our constraint.
Okay.
Got it? Because you've made that, you've turned it into a direction now. Okay. Okay, because it wouldn't be true for the other directions, would it? Okay, because if it's rolling on a plane, okay, if it's rolling on a plane and AY is normal to the plane that we have here, then that's what we got. And so then what is it operationally? What's creating that constraint?
Right?
Well, I mean, yeah, I mean, gravity's making there, but what's keeping it from falling through the floor?
Oh,
Right? It's a reaction force, right? So what do you want to call it? Or maybe something like Fy. Okay, and let's define it as what?
the reaction force not in the one.
Okay, all right, so give me something. Some F on what?
Yeah,
On BA from
Just say.
AB,
AB, excellent. Dotted with
and one,
AY.
A1.
Yeah. That's all right. Okay, that's it. Okay, so now, right, we've introduced, you know, back to what we did the other day, right? We've introduced an unknown. I don't know that. But we can find it. Right? Okay, what else? Rolling, right? And we're rolling, we're not slipping, yes.
The velocity of sorry, the velocity of BA is
Okay.
equal to the velocity of AB.
Okay. Fine. Okay, from any frame we want. Okay, and then
Equals 0.
equals 0. All right, so if that's the case. All right, that's our definition of rolling, so we're good there. All right, so now let's make it operational. What's doing that? What makes it rolling? What causes it to roll?
No.
So it's no slip, right? By definition, rolling is no slip. There's no such thing, by the way, there's no such thing as rolling with slipping. Those two are opposites.
Some initial conditions.
Initial conditions. So I want to know what physically is causing this to roll. Oh, I mean, yeah, I'm sorry, you got initial conditions, right?
We just start rolling the static friction.
Yeah, that's what I'm looking for. Okay, there's friction, right? Friction is doing it. In what direction?
So opposite motion is gonna work.
Is the opposite the direction of the motion it's going?
Yeah.
I should think about it.
Oh, it's the same direction.
It's got to be the same direction, right? The friction that's acting on the body has to be in the same direction that it's rolling. Isn't that wild? It's like, oh man, I got this static force.
Yeah, that's weird.
Isn't it strange to think about? I've got a static force, right, that is causing it to roll. So it's not actually causing it to roll, it's causing it to not slip. Okay, so reframe that a little bit. Okay, but it has to, because of balancing equations, right? It has to be in the same direction. Okay. And that's if it's pure rolling in that direction, right? So all right, so here we are, Fx. That's where we're headed to. Okay, we got to do a little bit more work over here. How do I isolate this? Because we're talking about a condition that's in the X direction, right? If we're isolating it, rolling in this direction, right? Similar, it's what Sarah, sorry, it's what Hannah was saying just a moment ago.
Oh,
What do you do here?
Oh.
Yeah, you start with AX, right? It's equal to- Yeah, this doesn't have to be, complicated, okay? And so then we get, right, it's F of B sub A from A sub B dotted with A sub X, right? That's it. Let's do the same thing on the next one. So it's velocity B sub A from A sub B in any frame dotted with a Y is equal to 0. And so F Y, I done this wrong, AY is Z. There you go, Z. Z is defined as F B sub A sub B dotted with AZ. Okay, okay. Stuff doesn't have to be complex, all right? But what we're showing here is that we've now introduced 3 unknowns we have to solve for in our equations. Okay, which means that no matter what the system is, you got to bust this thing apart, you got to break it apart so that you're exposing these forces. Okay, and then you have to solve for them. Okay, all right, there's one more condition. Okay, like, so we've dealt with this motion, right? We've dealt with this motion, right? Right. So what are we missing now? And it's what would define pure rolling. Here's a new term. Okay, this up there, rolling. Okay, below here, pure rolling. Like we've already said, rolling is not slipping. Okay, like that kind of makes it kind of pure. But now this is like extra special pure. There's another direction that we're not considering. Spinning, that's right. Okay. All right. Give me a way to mathematically express that rolling constraint for pure rolling.
Sorry, pure rolling is with or without spin?
It would be without spin.
Okay. I want to see what a rolling is.
Okay. All right. Yeah, think of velocity. Like
Yeah.
everything here except for this guy, right, is velocity, our constraints.
Yes, I think the omega about whatever is perpendicular to the plane
Okay.
is 0.
All right. So how do you express it?
Omega.
Okay.
That
All right.
is
A to B.
I think we said AY is the.
Good. Good.
Is equal to 0.
That's it. That's exactly it. Okay. So it's the angular velocity, and you're looking at the component in this direction, right, is 0. And so now, how does that actually happen? What prevents angular rotation? Would be a moment of inertia. That's all right hand side. We're dealing with the left hand side.
I feel like there's some Newton if you're not being acted on, you're not gonna do anything. Like if there's nothing to introduce that spin, we're not gonna
Something is stopping this spin. What is it?
friction.
It's friction. Okay, in this case. So. No. Is it just friction in one direction? Is it a force? Is it a force in one direction? No, it's 2, right?
Yeah.
There's a couple, right? So a couple, we also call those torques. Okay, right? So this would be the torque. Okay, and this is what we're getting at the moment, right? So the torque in the Y direction is defined as, it's gonna be the torque on B from A dotted with the A Y direction. Okay. All right, so that's pure rolling, is that there's friction there. There's some sort of friction there. It's kind of weird to think about friction at a point. Right, but how many things do we, I mean, there's no such thing as like actually point rolling. That's just not true. You always have a contact patch. Okay, that's where the friction actually comes from. But we don't want to model the contact patch and have to deal with all the friction that's there. We just say, hey, let's just let's just cut that stuff out. Okay, we're gonna assume that it's there. Great. And then you can come up with how much torque actually needs to be there, right? Then you can go off and you can do your experiments to find out what type of normal force is there to, resist the, to gain that static friction. Okay, still a static friction concept, but it's the torque in the y direction, okay, that's gonna prevent it from spinning. All right, so this is pure rolling. All right. All right, are we good? All right, so and we've set up now another equation you're gonna go find. Okay, another thing that we have to do with our dynamic system, another unknown by doing this. Okay. All right, so if we're okay with that right now, let's switch into gears. Okay, let's take a break, like 5 minutes, 65 minutes. We'll come back, we'll finish this thing out with gears. Switching gears into gears. See really quickly that we can put this thing in 3 really easily. Okay, so you got gear A and gear B. And we have another frame in. Okay. So now, I mean, quickly, all right, it's like, we've got the radius of these gears, right? So radius of A. We have RA, radius of A, RA, and we have radius of B, RB. Okay. Now, some other things that we know that omega into A is equal to the scalar in A into A. And then it has a direction, it's in the AZ, which is also the NZ direction. Okay, because you draw a frame on this, AX, Y, AZ, same thing here, right? BX, BY, and BZ. So then we also know that omega into B is equal to the scalar into B, and it's in the BZ or the NZ direction. Okay. All right, so the question is omega AB is multiplied times the radius of B is equal to omega, got this wrong, in B, get this right. Omega into B multiplied times the radius of B is equal to into A multiplied times the radius of A. Right? This is, it's our gear ratios, right? And so the question is it positive or negative? And that's really what gears boil down to. And all gears are this, but is it positive or is it negative? And how do you know? What's that? Negative? Scale. But we have a sense. We have a sense here.
Already do it. Opposite directions of rotation.
Okay. Yeah. It's negative. I mean, it is negative. It's not a trick question. Okay. All right. Is it possible for these to be positive? Not this one. Okay. Not this one.
Sure.
Okay. But we have to, but if something is rolling on the other, which is what we have here, this is rolling. Okay. We have contact and we have our velocity condition, our zero velocity condition between the two at an instant at a time. This is rolling. That's what gears do on each other. There are multiple situations where this is not negative. Okay. And you need to be able to look at a cluster. Okay. And be like, oh, negative is positive. How does this work? Okay. So we're going to slow it way down. Okay. And be way systematic, and we'll speed this thing up on how we actually want to do it. So I've got gear A, gear B, right? We've got all our same conditions here. That we've drawn here. You used your intuition about that, right? I mean, you actually went, okay, all right, and you got the right answer, right? That's what that's going to be. But how do we actually get there? So let's take these All right, I've got A naught, okay, B naught. I've got my point B sub A and my point A sub B. Okay, that's our points of contact that we have. Okay, we have a rolling condition. And the rolling condition is that the point B sub A, the velocity observed in some frame, all right, is by definition equal to the velocity of A sub B observed in that same frame. Okay, so when we get to choose our frames here, as a reminder, you have to choose the same frame. Okay, it has to be A and A, it has to be N and N. You can't be like N and F and like,
Mars.
why isn't this working? Okay, all right. So, all right, so it's the same thing. It's the same thing that we have. So it raises the question, okay, how do we calculate the velocity of A sub B? Right, how do we calculate the velocity at that point?
We gotta go to our efficient motion, right?
Yeah, we have to use some sort of equation, all right? And so in rolling, we end up dealing with these rigid body equations, okay? We end up dealing with derivative-free equations, okay? So we have to go to derivative-free equations, all right? Rigid body equations. So meaning you can't use the golden rule because this doesn't work for a vector differentiation. We're not differentiating anything, okay? So on the left-hand side here, we get that the velocity of B sub A is going to be the velocity of A naught in some frame plus omega cross R, okay? And so it's omega from that frame to A crossed with the position vector that goes from where to where? A naught to AB, okay? A sub B, right? And then this is equal to, so that fills out that left-hand side. And then on the right-hand side, we got to start somewhere. So somewhere on this rigid body, all right? If we know this point, we can start with that point. But we know that the velocity of B naught, hopefully, right, in that frame, plus omega cross R. And it's omega n to B, well, square to B. And then it's the position vector from B naught to B sub A. Okay, now these are good for continuous points and they're good for instantaneous points. That's what's nice about derivative-free formulation. Okay, because what is it that's instantaneous here? The velocity of A? No, that's just it. Okay, is it omega? No, that's continuous. It's this guy. This is our continuous vector, right? That's only good for that instant in time. Because as soon as you move this, right, I've got a new vector, right, that I have to replace that with. So that's what makes these things tricky. You have to use your instantaneous, you have to use the derivative-free formulation of getting the velocities of these points because it's only good for that instant of time. Okay, and the thing that's only good for that instant of time is the position vector. Okay, so now we get to ask the question, okay, all right, what reference frame makes sense here? Like what reference frame do you want to use? You get to choose any frame you want. What if we chose A? What's it going to do? Well, the velocity of A naught and A is 0. Okay, and then omega from A to A is 0, so that makes this whole side 0. Okay, a lot of times that's a nice idea. Okay, we like that. What about this? What's the velocity of B naught in A? Oh crap. Okay. Uh-oh. Okay, that one's not so helpful, is it? All right. But what about this? The velocity from A to B crossed with R. Right. This side, as beautiful as this side is, right? Everything going to 0. This side gets messy. I mean, now we're doing extra stuff that we don't want to do. So what frame do you want to choose? I'm going to choose N. Okay. So if we do N, then we get a 0 vector, right? Plus omega into A cross with R, A naught to AB is equal to the 0 vector plus omega cross with R. And this is from N to B, all right, cross with R from B naught to B sub A, right? Okay. And I mean, you're like, okay, all right, what are we doing here? It's just like omega cross R. This looks a whole lot like omega times R or R omega. okay, right? And I'm not gonna disagree with you, okay, but we're just backing up and being super systematic. Okay, so for our rolling constraints, we're left with this, you don't need to guess these signs, okay? Meaning that, okay, if I've got omega cross with R, then what, then, say here. And this is where omega, we said omega into A is equal to omega in A in the AZ direction, right? Because we've taken these things apart, okay? AZ direction, we said omega into B is equal to omega in B in the BZ direction, okay? Now, don't put signs on these, okay? These signs can flip, they can change, so just put them there, right? And so let this, the AZ and the BZ, give us the sense, all right? Okay, please promise me you won't put signs on these, okay? Don't try to use your intuition here, okay? So then, as we come into this, we now get omega in AZ crossed with, and at this instant in time, A naught to AB is what? Yeah, let me give that. So it's in X, in Y. Okay, it's in the in X direction, right? So it's R sub A in the in X direction. Okay, then this is equal to omega in the BZ direction. Okay, crossed with, and then it's R sub B in the negative in X direction. Okay, and we're not guessing on that. Our position vectors, we actually know that it's the negative in X direction, right? From B naught to BA. We're observing that. Okay, so we're not guessing in our position vectors, you're observing them. Okay, but when you have velocities and angular velocities, okay, like let the math fall out of that, let the sign come out of that. Okay, and then we do all this, right? AZ is the same thing as NZ. NZ crossed with NX is going to be NY or negative NY. Is that right? No, I'm sorry, it's positive NY. And so we get from this omega in a RA in the NY direction is equal to omega in B. So it's Z cross, so it's negative, and it's Z cross with X. And so RB. Yep, so I'm pulling my negative out, so we're good, right? And that's in the NY direction, okay? And then we want to pull those scalars out, so we dot it all, right? We dot it all with NY. And then this gives us omega in a RA is equal to omega in B RB, and we got a negative sign there, okay? All right, you're like, oh, crap, why would I do all that work, right? Just to show this. So let's do it a little bit faster here. All right, and so for this one, let's do it again. That's our fully systematic way of saying I have coincident points and I need to impose a non-holonomic constraint of rolling of a gear on a gear. All right, so if we do this again, we can say this way. I know that for this gear, I have to have an omega into A and an RA is equal to, and spread these things out a little bit, N to B multiplied times RB, right? And so now what we can do is we can just speed up the cross products really, because, all right, here they're separated again. Okay, always we're separated as we're looking at these and considering these. All right, for our angular velocity from N to A, all right, pull out your right hand. Okay, what way is it going? Okay, it's going counterclockwise, right? And so this, what direction is RA? It's to the right. Okay, what about this guy? Counterclockwise. Okay, and then what direction? To the left. Okay, so if I do my cross product of that to that, okay, counterclockwise to there, then I get omega in a RA up Do you buy that? If I do my cross product of this vector and that vector, then I get up because it's this vector crossed with that direction, it's up. Okay, and on this side, it's this vector, right, coming out of the board, crossed in that direction, so it's omega NB RB down. Okay, and so if that's the case, then we're seeing that these two are in opposite directions. So we see that it's omega NA RA is equal to negative omega NB RB. Okay, so we've done, so instead of like using our NX, AX, AZ, instead of using our bases, we're just given directions. Okay, yeah. Right, and now we have vectors here. Yeah.
In this situation, those two gears are separate.
Those two gears are separate. That's right. And so then when they touch each other, right? When they touch each other, we're now applying this constraint. Okay, and we're saying this is the velocity of that point. That's the velocity of that point. And separately, given the sense of these vectors, they're going opposite. Okay, so for them, and that's not permitted here unless they're slipping. And because they're rolling, we have to put a negative sign on one of them. All right, conceptually, that's what's happening. All right, so then just to do it even faster, okay, you can just do it this way, right? I'm just saying NA RA and then omega in the B RB. Okay, and now with this, right, just draw them right on the gear, right? It's the velocities of those points, okay? And then we say they're opposite directions, so therefore, that's where we get our R omega and A RA NA is equal to the negative RB. Right, and that gets back to what you were doing earlier, like, okay, my gears have to roll on each other in this way, right? But here, we're not thinking about how the gear rolls. We're thinking about what is different about this. Okay. Like we wanted to build some intuition about this, but instead of thinking about, all right, that's how my gears are rolling. What are you thinking about now? What am I trying to push you to think about? It's not one gear pushing the other gear. It's the velocities of these points. Okay, we're back to our definition of rolling. Okay, because when we think about gears, usually we aren't thinking about rolling. We're thinking about how a gear spins. Right? I mean, that's how I think about it. Like, you know, if I'm looking at this, I want to see how this spins. How does this thing spin? But if you think about how a gear rolls, which is what we have here, yes, they're spinning. Okay, but they're rolling on each other. Okay, think about how they roll, you can get a lot more intuition about how a cluster moves. Okay, so let's do that. All right, so the super fast way here, and by the way, we had an important step in here, is that we had to define a common frame, okay, that we were doing this with. Okay, and that was the step that I don't want to negate here. Okay, when our two gears are fixed in N, please use N. Okay, but what we're going to be actually looking for is, well, we'll do it here. Let's do a more complex cluster. Okay, because you're always going to be copying down a ratio, and then you're going to be asking the questions: positive, is it negative? Positive, negative, and then how you answer that question for the positive and negative is looking at the velocity of the points of contact if it's not rolling. Okay, so let's do it this way. All right, so let's draw this cluster. So we've got let's see here. Let's get the gear ratio from A to B. It's got some theta. This is bar E that is connecting gear A, and it's connecting it to gear B. For this, we have a radius r sub b, we have a radius r sub a. Okay. All right. So we have a naught. A naught is fixed. So r a naught. I got my b naught. B is a celestial gear that revolves around A. All right, can you tell me real quick how many degrees of freedom we have here?
Mhm. I think, yeah.
One. How do you do the game for years for degrees of freedom?
I make it strong and sweet with guessing. Yeah, that's how I feel about degrees of freedom so far.
Yeah.
That's that.
Yeah.
All right, so it's 2 degrees of freedom here.
Oh,
I know, it's challenging. Okay, so we want to find the gear ratio. Ratio from A to B. Or the, okay? Or between A to B. All right, so let's work this out. I'm gonna work it out over here. So we know that B is rolling on A or A is rolling on B, right? Anything that's in contact with each other is rolling. And so let's write it as the velocity A sub B by definition is equal to the velocity B sub A. Leave this blank. Okay, leave our reference frame blank as we're doing this. So let's do this left side. Where do you want to start? I think A naught's a great spot. Okay. So you always need to start somewhere on the gear, right? We're going to add the velocity or the angular velocity, right? Not filling in the reference frames we're making our observations from. Square there, omega A cross R. And then this is R from A naught to A sub B. And then equal to on this side, the velocity of B naught. We know that point because it's given to us, right? That's the only point we know on B. B naught plus omega cross R. And then don't know our reference frame that we want to use yet. We need to go B naught, B sub A. All right. Now we can, this is the important part. Okay. This is true for any frame because it's the rolling equation, right? This is our rolling constraint, non-holonomic constraint. Choose your frame. What frame do you want to use?
E.
E. Why do you say E?
Because it looks the scariest. I don't know. I don't actually want to do E. That sounds
It
scary.
looks the scariest. Okay, we have 4 that we can choose from. Okay, we have N, we have A, we have B, and we have E. You like N, you like N. Okay, if you're motion genesis, use N. Okay, all right. We're not motion genesis. He's got an angle defined. Oh. Right. Spooky. It's really not that spooky. But E. Why? So E is the right answer. Why? Why is E the right answer?
I think it almost takes 7.
Does it?
Well, is A actually moving here? Is A fixed?
Oh, maybe.
What do you mean it's A
Maybe
move?
it's
A.
Oh, so
is the just
No,
rotating?
A is absolutely rotating.
Yeah.
Yeah.
If you
I mean, I've got a
choose-
gear that's spinning and a gear that's spinning and an arm that's spinning.
But yeah, I think he's asking is AO fixed in
A is not fixed in there.
AO.
Oh, is A? Oh, I'm sorry. Is AO fixing it? Yes, yes. AO is fixing it. Sorry. That's what I did finish drawing there. There we go. What do you got?
Well, if you fix E, then it seems to me at least like the problem would just be like regular, just 2 gears.
Oh, if I fix E?
Or not fix E, but if you look at it.
Yeah.
It's just.
So that's what we're saying here. So by choosing these frames, and so you got it right. If we observe it from, that's what we're asking. Like, where do you want to be to make those observations? Okay, because if you're on N, you're watching this cluster do its thing and saying, whoa, right? If you're on A, like you're like, okay, I got an arm going around me, right? And then, oh, there goes B, right? Can you imagine hanging out on that gear, right? And if you're on B, it's like, right? You're a celestial gear. And so now you're at the mercy of E and then whatever A is doing. But if you're on E, right, now that's a little bit, I'm revolving, right? I'm revolving and I'm not spinning. But
And
E-
E is gonna be ugly, right?
But into E is gonna be theta. You got theta, it's just
Oh.
theta dot, the negative in Z,
Huzzah.
right? But the point here is that you're asking the question, how can you observe A and what is the best spot to observe both A and B? Well, what's connecting A and B? E. Okay, so what's this? Okay, put your E in there. Choosing E. Right? And now that we're choosing E, guess what we get to do? 0, 0, and we're back to R omega, R omega. Oh, isn't that great? Okay,
Yeah,
right? And so now I've got omega. Now it's R omega, but it's R from E to A. Okay, and then RA, and then omega from E to B, RB. Okay. Positive or negative? We're back to the same thing that we had earlier.
Should have done
Okay, negative. Why is it negative? Right now, what are we doing? We're holding E steady. Okay, once you start making your observations from E, you're saying, I'm on E. Okay, I'm not pretending I'm in N. Okay, I'm holding E steady. Now let's look at this, right? That direction. That direction, they're opposites, so it's negative. And so when I said that direction, okay, I was talking about this is the velocity of V sub A in E, right? Because that's what we have here. This is the velocity of V sub A in E. This is the velocity of A sub B in E. Right. Right. Does that make sense? So in that case, it's B sub A and E. This is the velocity of A sub B, and they're opposite directions, right? If they're not touching each other. Then as soon as they touch each other, just that direction. Okay. All right. So here is, how many degrees of freedom do we have in this problem?
you said two.
Yeah, there's 2 degrees of freedom in this problem. So if there's 2 degrees of freedom in this problem, we still got to go chase something else. We got to chase another equation. We need another equation out of this. And how do we get there? So degrees of freedom. That was P is by definition N minus M. So if this is the case, right, how many motion variables do we have? What's that? Visibly, I guess that's,
In this
I put
picture.
one in there. Yeah.
Yeah,
So we gotta have a couple more. We gotta have something about how A spins and how B spins. We already dealt with E, right? So we've got this guy. Right? Because we know it's gonna be theta dot in Z direction, okay? Negative. And we would get that using our angular velocity template, right? We would say plus or minus the time derivative of the angle between NX to EX. Okay, right? NX to EX gives us something in the negative NC direction due to our right-hand rule. Okay, so that's how we get that. Well, what about, but we actually have 2 more variables, okay? So we have this guy, which is going to be omega in the AZ direction or NC direction. We have omega in B in the BZ direction. Sorry, a little cluttered here. All right, so how many motion variables do we have? What's that?
Three.
So three, right? So three. Boom, boom, boom. Okay. And I kind of asked you, it's like, oh, can you look at this and come up with?
I
Can you,
didn't think about eight rotating.
yeah, A rotates.
Yeah.
So we get into this question, like, you know, if I move A, does everything else have to move?
Mhm.
Right? I can move A and I can hold E steady. Right? Okay, because if I moved A and everything else had to move, that meant this was a 1 degree of freedom problem. Right? Just like in our 4-bar. If I move E, does everything else have to move? No. Okay, because I can fix A, and like move E and B can do all the work here. Okay, I can fix E and N, I can spin A and then B will move. I can fix B. Yeah, you fix B and you're stuck, right? So that tells you B is at the mercy of A and E. Right? So just intuitively, are you following me here? Okay. So this tells us that there is one motion constraint so that there's 2 degrees of freedom. Okay. What was that motion constraint? This guy right here. This was our constraint equation. Okay. And so we took this vector equation and then we made this is our scalar constraint equation. Right, so we boiled all that down to this. Here's our scalar constraint. Right, so that's our extra equation we had in here. But now, do we know this? Omega E to A? Or omega E to B? Like I like N. I mean, that's where we started. So ooh, I like omega N to A and N to B. Add stuff.
Yeah, like we can get there.
So we got to get another equation because what we did here is we introduced, okay, based on our velocity constraints, okay, we have now introduced 2 unknown variables. Okay, so you see how you got to be careful not to let this get away from you. Okay, you got to make intelligent decisions. Okay, but by our constraint equation, which we needed this one more equation to make these 3 motion variables turn into 2 that are connected to each other. But in doing so, we introduced 2 unknowns. Right? So how do we find those? Tom just said it. Okay. If I want this guy, right? Really what I want is this guy, right? Because omega E to A is equal to the angular velocity from E to A in the NZ direction. By that? Okay. All right, then that raises the question, right? Where do you get omega E to A? And that's going to be using the velocity addition principle theorem. You got it?
Yeah,
Yeah. Close enough. All right.
I can never remember the combination of words.
It's all right. Okay, equation, theorem, principle.
Yeah.
Yeah.
Law.
Right. We had a good discussion. I think it was in the human movement class. We talked about Thomas Kuhn's structure of scientific revolution. Yeah, just do it. I need to reread it, honestly. All right, so
Sorry.
Thomas Kuhn, structure of scientific revolutions. You wrote it in the 60s, I think. Might have been, yeah, I think it's 60s. That's where so Kuhn died in
Spell his last name?
Kuhn. Sorry, yeah, that's not a common one, is it?
Yeah.
Yeah, Kuhn. He was a philosophy of science guy, and the book isn't that long, but just impactful, hugely impactful. I mean, like we used the term paradigm shift because Thomas Kuhn. We used the terms like theory and law and that kind of stuff because of Kuhn. Like we now, in kind of differentiation between hypothesis, theory, law, and so forth like that. But the main thing with Kuhn, and this is what I love, which is very countercultural these days, is the whole idea that what is the science, right? He says, ooh, watch out, because how paradigms shift is they shift rapidly, and it goes, right? And that was the point of this book. And so anyway, that's where we get those things. So you got to watch out for. Yeah, got it. You got to watch out for that stuff. Okay. Right. Yeah, and I think that's the kind of current. That's what kind of got on my radar again, like the past few years, because I heard everybody talk about the science. The science is settled. I'm like, ain't no scientist that's worth the salt gonna say that, right? And that's why. So, so here, right here, we're even Newtonian. Okay, right. So what was that paradigm shift?
From Newton to Einstein?
Yeah,
Yeah,
that's huge, right?
yeah.
Right, Newtonian,
for
and
me.
you've
I
taken, I mean, you've taken the relativity classes. Yes.
Much,
Uh,
not a real relativity.
okay,
Real time to think about it.
what's that?
Going through relativity stuff.
Yeah, so, but that kind of stuff matters, right? When we start working in quantum physics, like that matters, okay? But like what we knew as the science, right? It just didn't count anymore, right? Well, we can still do it for this, right? Which is really nice. You can still send people to the moon with this.
Yeah.
Right, I like that. So, all right, if I want this, so read it, it's a wonderful book. And actually not that hard to read. So, all right, E to A, what are we doing?
E to N and then.
This is how I set this stuff up, right? I want to start at E, I want to get to A, you want to go to N, and then you want to go from N to A. Okay, all right, boom. All right, here's another equation. Once you do the dot product in Z. Okay, this is our next scalar equation. All right, and then we need to get omega E to B. And then, because we're going to dot this within Z, then we need to get omega E to B, and we're going to go through so E to N plus omega N to B. We're going to dot this whole thing within Z. All right, and now we have two more equations because we introduced two unknowns into the system. All right, so now with this planetary gear, okay, excuse me, with this planetary gear, we have everything that we need to solve this system. Okay, and you can plug all this into motion genesis and you're good to go. Because we now have, let's just, and this is what you got to do with these gears. We got to count them up. How many motion variables do we now have? Okay, I've got theta dot. Well, theta dot, I'm going to call this omega N to E. Okay, because that's another thing we said here is like I've got an E to N, which is going to be the opposite from N to E. It comes from that vector. Okay, so I've got N to E, I've got omega N to B, right? That's from over there, right? N to B, or from there, I've got N to A. I've got these three. I've got omega E to A right here. And I've got omega or right there. And I've got omega E to B. I have 5 motion variables that you got to handle here. Right? And so now, how many constraint equations? I'm going to say constraint equations. Let's go back to our piece here. 5 motion variables. And we know there's 2 degrees of freedom. So how many constraint equations? 3. Okay. And those 3 constraint equations are this, this, and this. Okay. Can you see how those are constraint equations? Like, what is a constraint equation when we started our formulation of constraints? We're saying I'm going to restrict the motion in this way. We did it using velocity, right? Our velocity in rolling, okay? We've done it using our points, right? You can't. This case would be like the velocity of this guy, that you can't go through the floor. We talked about our 4-bar linkages can be velocity, but it's motion. We're making comments on the motion and we're restricting the motion in some way. It could be with a position vector, right? That's restricting the motion, okay? And here we're saying, I'm going to restrict the motion this way. I'm going to restrict the motion this way, even though we just call it an angular velocity addition theorem. Okay, you're still restricting the motion. And then I'm going to restrict the motion in this way. Okay. And so we had to come up with those extra equations because we introduced those new variables. Right. Okay, so I mean, gosh, we can make this thing as complex as you would like. Let's do one more level, just to kind of get in the groove here.
We make it as complex, we can also make it as uncomplex as we like, right?
As
How complex I like is very limited.
It's all the same question.
uninteresting.
Oh, for sure.
Right. All right. So there we go. All right, so now here's my next system. Okay. So you can do this, you can throw a gear C on this. All right, let's do one more. Okay, let's make this a hoop. On the inside of that. And then let's add a bar F. And then we'll put gear D here. There we go. All right. Let's do this. Yeah, it's exciting, right? Okay.
I'm having a hard time picturing how the bar and the hoop and the disc are staying together. Like,
Oh yeah, so you can put some spokes out here.
What happens when B hits C?
Oh, well, that's deeper. Right, you can drive that from, well, I mean, sure, you can. Well, but you won't, because this can be a thick, this can be twice the depth as that, and that's running below it, and this is gonna go right at the top of it. Does that make sense?
I think
Okay.
so, yeah.
All right, so what are we going here? Okay, so we got to do reference frame to reference frame. Okay, as we're handling this. So I got a planetary, so this would be a planetary here, right, on the inside of this. Motion variables. All right, I've got omega into A, right? I got omega into B. I got omega into E. We've already handled those in this system. I've got omega, we could say it's like omega A to B. Right? We could get that, we can roll through that by going through E, right? Because we chose that frame. Because we also have omega B to E, we also have omega, I don't have a C to E. I got an A to E. Yeah, A to E. Okay, we got those guys. All right. And then what else we got? We got omega E to F, right? And then I've got an omega D to B, or we could say D to F. There we go, D to F. Yeah, that would do it. I think that would do it right there. So it's, I've got eight motion variables. Say again, did I miss one? Did you say N to C?
Do we need?
And C is just not represented.
Oh, yeah, it's not, is it? Let's do N to C. All right. Okay. All right, so now it's actually in these situations. So let me come down here and let's focus on this for a moment. Okay. I've got, call these something else. Let's see. B naught, B, F, and D. All right, so down here, let's get this one right here. That's D inside of B. Let's handle that for a second, okay? So tell me, I don't think make sure I got that on the video. Excellent. So tell me, just from when we're working with D and B, right? We're not thinking spinning anymore, we're thinking rolling. So what is the motion constraint?
Yeah, the velocities are gonna be equal at all the contact.
Okay, so the velocities are equivalent at the point of contact, right? So that means we have to say, so what's the equation? Okay. D sub B, yep. So D sub B, eddy frame, is equal to the velocity of BD, right? By definition, that's what we got. So let's work this thing out. Okay, so we're gonna end up with an omega. Well, what frame do you want to use? Yeah, I want to start thinking about F. Okay, so we're gonna do an omega R. And it's gonna be omega, so this, if this is the velocity here, it's gonna be the velocity radius D is equal to omega R, what? B. So it's omega, it's gonna be and B.
This is like a thing here on this line. Is that it's too complicated to have a second radius that we can do it.
Say it again. What do you mean?
Like RV, it's like the.
Oh, yes. I see what you're saying. I'm not making a distinction on the thickness. So yeah, right. Good question. Okay. Actually, it wouldn't matter. No, so RB could just be to the inside because that's the point of contact for both of them. That makes sense? Yeah. Okay. So thin, thick, it doesn't matter as long as that dimension goes to the inside of the inside of the gear. Okay. All right, so yeah, what reference frame? Yeah, I'm gonna choose that. Okay. All right, so I'm actually gonna choose the F. All right, so we're left with this equation. All right, and so C and D both have fixed points in F. That's why we chose that. Ryan, we got crazy on you while you left. So, all right, and so we see this. We're going to see that from this. So the velocity on one side, the velocity of dB, all right, is equal to the velocity of dO. What are F's in there? Right, plus omega F cross with, sorry, F to D cross with that position vector. The velocity of BD and F is equal to the velocity of F in B naught omega F to D cross with that position vector. All right, so we're choosing our F's. So these to be 0 and 0 vector. And then we got our R. We've got our omega cross R question now. Okay, and so for our omega cross R, what's happening here? We're looking at F. Okay, we're saying I'm holding F constant. And then I want to, with F being constant, okay, what's the direction of the, I want F constant and I want to separate those gears. All right, so let's make this big now. Right, F is constant. There's my gear D, and then we're saying I'm going to separate these guys. All right, there's my spokes that are going out to it. B naught. Okay. What's my so here's my point. There's my point. I've just separated them. Okay. What is the direction of the velocity of B sub D in F? Because we're dealing with this. It's omega cross R. Okay. But D sub B, this is my point. D sub B, right here. Okay. It's omega cross R. We're just making sure that everything, okay, is going to be in the direction that we're making no assumptions. Okay, so omega, what is this? Omega F to D is equal to omega F D in the
No, and
Yeah, or FC, right,
Oh, sure.
NZ, FC, but it's a two-dimensional problem,
right,
okay?
easy.
Okay, so what direction will we draw in here for the velocity? It's this way, right? And that's my velocity in F of V sub B, okay? Good? All right, what about this point right here? V sub B, all right? F, there's my frame F. That's wild.
Think, on something very uncomfortable.
So V sub D, right, taking away all this stuff. Taking away all this stuff, okay, V sub D. And so I have to handle this, right? It's my omega F to, oh, did I do the wrong thing? Sorry, this is F to B. Sorry about that. Omega FB is equal to omega F to B in the FC direction. Okay, right? And so here my omega cross R, looking at my vector, okay, is in what direction?
Yeah.
It's in that direction, right?
Close.
The velocity of BD and F. Right? So what is our gear ratio? It's gonna be, right, R omega, oh, I've got them over here. Look at that. It's omega R omega R, right? That's our F to D. F to B, is positive or negative? Positive. Okay. Hear me now, believe me later, right? This is actually what happens. You can get positive gear ratios between gears. You're gonna see that they end up happening in celestial clusters like this. Occasionally it happens like some other bizarre things that happen. Okay, but these like interplanetary gears. Okay, that roll on the inside of another gear, you end up with positive gear ratios, right? And the reason why you can figure that out is because of the right hand rule. Okay, how you make this okay is we'll write down the steps and then it's just not okay. It feels really bad, doesn't it? Like what just happens? What just happened to me? Okay. All right. And so, all right, I want to write down these steps and we'll get out of here because it's the class coming in. And we can talk about this more in office hours if you want to. And you were going to solve a cluster that's in 3 dimensions. So 3 dimensions is easy coming out of this because everything is at right angles. Okay. And you can just do the cross products and it's a question. So once you start tipping a gear up, right? These are the other situations in which you're like, ooh, okay. How does this connect to this, okay? All right, step 1. Okay. Identify the reference frame that the gears share. Critical, okay? The frame that they share might not be close by. Okay. Number 2, copy down the ratio. Okay, in this case, well, it's always omega R omega R. Okay, but after you've identified that reference frame, you're able to put in right where you're observing that from. Okay, step 3, choose same or opposite direction. Okay, plus or minus. Okay, and we're making that assessment from, and here's why it's uncomfortable. It's like you're making that assessment from another frame. Okay. All right. In this case, is it possible, right, for this to be spinning and this to be spinning in the same direction? Absolutely. Okay. They even have to be if I'm right here. Because if this guy is just, can you picture it? Right? If this guy is spinning, right, and we're holding this frame fixed, it's spinning that same direction. Okay, so just kind of slow down and build up your intuition about this. Okay, the problem that you're going to be doing with the gears is 1114. It's a it's a big cluster, okay, it's gonna take you a little bit. It's worth it.